Okay, something else happened now. Ah. Sorry, just it was working. Okay, so let me start again from the beginning, because anyway, I have to record it again. So basically, all I'm doing here is running a linear regression model. So for that linear regression model, I am setting up the ML flow, I'm importing it. I am saving the artifacts in one particular file, which is the weights and biases and all. And I'm creating a Python function, and all those things are stored in this MLflow UI, which you can open in the same way you open the TensorBoard. And once you have that, basically you need to do MLflow model serve of that. So that's something I'll do here again. So for some reason it failed earlier.
You want to try to jump over to another VM?
Yeah, I can do that. So I think I can go to.
Try number 12. I'll look at it real quick. Let's see if anybody's on 12. There might be one person on 15.
Okay, so let me close this. I don't think that would be useful anymore. So
oh, you know what? 12 is full, or yeah, 12's got people on it.
So 15 it is?
14. Do you want to try 15? Yeah.
15. I'm just repeating all the steps I did earlier as well. So once I have that, and then I can go to train books part 1 deployment. And then I can do MLflow UI 8000. That's going to open the MLflow UI. And I need to open that. So I need the UI to get this model path. That's the easiest way to get it. And once I have that, I can go and then MLflow models serve -m copy paste 5. Let's just hope it works.
Yeah.
Otherwise, I can show the working version I had last night. So any questions so far?
Is anyone else struggling to get their ML flow to run?
Or did anyone get it working? Can you give guys a thumbs up or something if it's working, or if it's not working, thumbs down, something like that? Ah, it's working. So some GID issue or something it was saying in that one. So probably something happened there.
Yeah, there had been something I saw in the container where it was running, the GID was 1,000 in the Cybers container.
Uh-huh.
I think it's only 100 for the GID in the Jupyter lab normally.
Right.
So we could sort that out later.
Yeah.
Did it work?
Yep, it did. So once it is, so let me zoom in. So once it's running, it's going to have something like this. So basically it's going to say model initialized. So that means that it is, the server is running. So since the server is running, I can perform any queries on this server. So for that, basically I have this simple thing here. So I'm going to, so right now I'm running it on port 5001, right? So once, since the server is running, I can request some information from this server and get it. So I just provide the URL here. So that's 127.0.0.1 5001 and invocations. Invocations is just to just as something it needs for getting the query. So now I create a NumPy array of some random 6-dimensional variable. I dump it in a JSON data, and I post this request to the URL with the JSON data and the header, and I get the output from there. So this output, if the REST API is properly deployed and everything, then this will respond and give us saying the output is there, and then the output is going to be this, which I'm converting. So again, as I said, I can send information because this is a URL and I'm sending the data through a URL. So I can send it either through a data frame or a pandas data frame or this thing, JSON data. And using the JSON or pandas data frame, I can get the URL. I can get the response, and from that response, I'll have to again convert that JSON back to NumPy array, which we like to look at. So that's what I'm doing here. So I can run this now. So I'm doing this for one sample case and a batch of samples as well in both the cases. So you can see that now it ran, and it's able to give the prediction of both for a single sample and a batch of samples. So did anyone get till this point, or are you guys facing any issues?
Hi, Aditya. Can you show me again about like how you open the ML flow, like the command to open the ML flow?
The ML flow UI you're talking about?
Oh yeah, okay.
Yeah. So this is the way. So you say ML flow UI and then -- port 5000.
So
And
sorry.
yeah.
So does this port matter because you were setting the 5001, correct, in the notebook?
Yes, that's correct. Both the ports. So 5001 is for the server. So I'm running a server as well, right? So this is for the UI where I'm tracking all the information. So here I'm tracking what the model is and all. but ultimately I am creating a REST API server for deploying this model.
Oh, okay, I got it.
Okay,
Yeah.
so this model is deployed using another port. Both the ports cannot be the same, so that's why I have two different ports. Same way, if I'm running TensorBoard, I cannot run it on 5000 or 5001. I have to use some other port. So I'll be using say 6000 or some port for that.
Okay.
Any other questions, issues? Have people been able to come to this point? A thumbs up or something? If you guys could come till here. Someone says no. Can you tell what is the like if you're facing an issue, what is the issue so that we can help you? You can unmute and speak as well if you want.
Smilahim, is that you with the no?
Yes, can you please change the terminal, change back to the terminal where you started the ML flow here?
So the ML flow server model, sir. So that's basically this.
Yes.
So I'm saying
yes.
ML flow models serve -m, and I need to give the model URL, basically where is the model present. And for that, I am going to the ML flow UI. And here I see the ML model here is in this path. So I'm going to copy the full path of this. So there's a copy option here. I copy it and then I paste it here and then I say port 5001. Okay. And then
This is my first time ever seeing ML flow. So ML flow starts as a dashboard first.
Yes.
And then once you have that dashboard running, you're then looking in the dashboard and finding the specific model that you've just initiated. And then you get to copy that special URL. Okay.
The dashboard comes from this ML flow UI. So I had another port here, right? So I just say ML flow UI and port 5000, and that opens up another dashboard. The opens up the dashboard. So
the dashboard, yeah.
I am saying 5000 here. So I go back to here. So this is nothing but TrAC train, whatever number you had, user, and then your username basically proxy,
yeah.
and then this. So just keep in mind one thing: if you don't put the / and just put it this way,
You won't find it.
it won't give you anything. So you
Thinks
need
it's a
the
file.
trailing, yeah. So you need a final / as well.
And so then the Numpy deployment there, is that the one you just did, or is that?
I just
the
did that.
Default one. Yeah. Okay.
No, I just did that, right? So I ran the deployment here.
Yep.
So I saved the model here. So I'm logging the model, and that model is what I'm loading there. So right now I am just logging everything in my local machine, but ideally you can create a ML flow server, tracking server in cloud, and use that SQL database or Postgres SQL database, and basically log all the models in that cloud server as well. So any questions? I do have another example, similar examples, doing the same thing. Instead of a NumPy, I do it for a proper PyTorch model as well. So that's basically this guy. So in the same folder, there is a PyTorch mnist training.py. It's doing the same thing. It's training for mnist. Mnist is the handwritten digits dataset, and the training pipeline and all is pretty much similar. Just that I am also tracking all my experiments by the ML flow tracking thing here. And I create the network. I can say, write all the histograms if I whatever I want in TensorBoard, and then I can also log all the metrics, add the scalar, add the log metric, and all. I can save all those things, and then I can create a wrapper, model wrapper for the PyTorch function as well. So here I am using this for predicting for a PyTorch model, and that's this PyTorch model wrapper. And I can even add additional dependencies, whatever I want, using this functionality. And this ML flow. So then I again do the same thing of log artifacts, and I log the model as well. So, and where does it log it also, I can save that. So what I can do is I can open another terminal. Sorry, I'm going to a lot of terminals today, but TrAC train 2022 notebooks part 1 deployment, and yeah, so deployment, and then I can do Python PyTorch training mnist training.py. So this is going to train the model. I think this is going to run for 10 epochs. Yeah, so these instructions which Tyson is giving here is something I've also, I think I provided it in the deploy NumPy here. That is, yeah. So you can get the, yeah. So yeah, this is the way you run it. So anyone else facing any issues from here? Any questions?
Can you go back to the ML Flow dashboard again? I have questions.
Yeah.
So you come in here and we can see our experiments.
Yes.
And then we can see that it's running a type of model. And then what's underneath models? Is that just another, at the very top of the screen, there's experiments?
Yes. Yeah, so this is something which basically means that, so right now I'm serving a model in my local machine, right? I can, if I have a registry, a database registry.
Oh, I see.
I can
get models.
I can publish the model there.
Yeah. Okay. So you would you either upload models from there, or you can get models down.
Exactly.
Okay.
That's right. So that's exactly what that is going to do. So that's why if I show here, if it would say that the functionality is not available, but yeah.
So normally you would be running this from the ML Flow cloud service or something, and that would be connected.
Yes.
Okay.
Or basically, you'll be serving it using a database. You need a database where you'll have serving all those things.
Right.
Yeah. So as you can see right now, the PyTorch experiment is still is running, right? So because it's running, or it ran, it has created another folder here as well. So let me close this. So it has created this thing. This also is, so as you can see, it is also saving the test accuracy, test loss, all the parameters it needs and all as well. And I can always go here, click on this. So I can get all the parameters it is saving. So it's saving all these parameters it ran with. And these are the metrics it is logging. And what I can do is I can come here, copy this path. Again, I can do ML flow models serve -m, paste the model, and then -p or -port. And then since I've already used 5001, I'll use probably 5002. Right.
Did you get the full path?
Yeah,
does
so
it need-
you don't need to give the ML model, basically. So you need to give the folder path where the ML model file is there.
and is that creating yet another conda environment?
Yes,
Wow.
with all the dependencies. Ideally, it creates a Docker container with all the things so that you can deploy it as a separate model as well. So that's the ideal. So that's the reason why there's a registry. So in the registry, everything is in a Docker container. Since I'm running it in my local machine, it's creating just a conda environment.
So Aditya,
Yes.
do you need to keep track about what port you used, correct? Because I just not try if I mean, like if I directly use this server to download this model, like to get a Kona environment, if I didn't do the port, and I think it automatically come to the 5,000.
Yes,
which
that's
is
correct.
it didn't like get it correctly. So every time I need to get record like what port I use, correct?
I mean, it's better to keep record of what port you're using. But ideally, if you're using the same port, then it will give you a warning or an error, and it won't allow you to host the same, like using the same port, basically.
Okay, sure.
So yeah, just like we ran for the deploy NumPy, we can run the same thing here. So I'm just down. So for this, for performing inference of MNIST images, basically I need to do this one step of basically getting the MNIST images, because MNIST images are not available with us. So we need to do that. So probably let me actually do it here itself. This is going to save all the, unpack all the images which are there. Right, so it got the images. So I have to do is basically go to that folder. So I'll just say /mnspng, and I'm going to get the testing images. And for those test images, I am just going to load the top 100 or the first 100 images. And then 1 second, so something went wrong. Obviously. So it is mnist.png.
Is it not like your relative path? Oh, it's different.
There you go. So, and then now I can get this. Oh, so yeah, one thing I missed. So I need to get the run ID. So there's another way without doing the REST API, you can do the prediction as well by loading the model directly. So you can do mlflow.pyfunc.load model and load the model itself directly. So for this, I need the run ID. And that run ID is nothing but this guy.
Mm.
So I can get that run ID and then just run it as well. So, and that's what I'm doing here. So since I'm doing that here, that case is basically REST API where everything is deployed in a cloud and then you're just going to query and get the result. Here it's just locally doing the inference using the PyTorch model itself. And here I'm going to do that with a REST API if I want to. So yeah, so that's so this is 5002. So that I'll use that here. There you go. Any questions so far? So I'll probably let's take a break now. It's already 53, so we can take a break now and then start it again at 3 o'clock and see where we go from there. In the meanwhile, if you have any questions, then I can answer those as well.
This is the part where we all have to bind together so we can get through the last part of the workshop.
Yeah.
We get a coffee or some sugar. So when you ran that REST API just now, it looked like it wasn't ready.
It ran.
Did it run? What the
The
output
REST
was?
API was already ready here. So
Oh, that was just in your, I see. It was just in your cell. It would output that.
Yeah.
It says, yeah, if it's an error, it says it's in progress. I read that. I thought that was the output.
Okay. No, that was something I had just for error handling.
Yeah, that's good. Yeah.
Yeah. So
Yes.
I was running the PyTorch inference. I had some error. Is saying something is some I think some variable is not defined something.
Or run ID is not valid.
Not run ID. I think it's non is not defined.
You need to give the path correctly, the path here of where your MNIST PNG is stored, the data.
Okay.
So if you give the path correctly, then the test images and all will be available. Otherwise, you could get an error for that.
Okay, I try it again. Yeah, sure. Thank you.
All right, let's get started again. So this is probably the last leg or so which we'll be taking, and then we'll see how it goes. So till now we looked at how model deployment works and everything and all. So this last section on intro to GPU computing and the setting up of the work environment and everything. This is more for helping you guys understand the nitty-gritty details and some of the hardware and software related obstacles one would face when you're running deep learning models and all. So for this reason, we wanted to cover a few basic understandings of why GPU computing is required, or why are we doing all these things, where can you run different things and all. So these are different things I wanted to cover in the second part of the tutorial, so which I'll do now. So let me close these different sessions and then start with the other part. So the way I would start basically this whole part of the GPU computing and all is that why do we need GPUs at all, or why are we using GPUs at all, is something to understand, right? So let's take some basic input like simple libraries, and I'm going to take just simple A and B, two matrices. Both of them are 32 cubed, so 32 times 32 times 32 dimensional big matrices. I could go even further. Maybe I can even say 128 times 128 times 128. I don't know if the VM will cry or not, but let's try. And what I want to do is I have A and B, and I want to compute the maximum of each matrix. So I want to find out what's the maximum value of element-wise maximum of A and B, and then put it in C. Basically, that's all I want to do. So a simple operation like this, if I implement this without using any NumPy or any other operations, just using some for loops, that's basically 3 for loops here. So I write that 3 for loops here as for I in range of A dot shape of 0, J in range of A dot shape of 1, and K in range of A dot shape of 2. And I'm going to compute the maximum value of both of them and then return it. So when I run this block, sorry, my bad. When I run this block, it's going to take some time probably. Let's hope that it gets done quickly. So what's going to happen is I am using for loops defined in Python. And basically, as you can see, so this ran for around 7 runs. So it ran 7 runs for each of these loops, and then gave saying that this one particular function takes about 1.47 seconds to compute, plus or minus some 16 milliseconds or so. Now, the same thing which I'm doing here can also be done using np.maximum of A and B and return that in C. Okay, let's see how fast this runs. So you can see that what took earlier 1.47 seconds is now taking 17.5 milliseconds. Can someone tell me why is it so? For those who are not probably expert in programming. Anyone over chat?
You using a function?
No, I'm using a function, but what makes the np.maximum function much faster than using the 3 for loops I wrote here?
Is there parallelized or vectorized?
np.maximum is not parallelized or vectorized. The difference is that np.maximum is written in C or Fortran and compiled, and then we are wrapped up so that we can use it in Python. So that's the difference between how an interpreted language versus a compiled language has a performance difference. Yeah. So np.maximum is so fast only for the reason that it is running in C++. Or C.
Is it C++ or is it Fortran?
It's C, actually.
Okay.
So NumPy's half function, older functions are all in Fortran, but some of the functions, these functions are in C actually.
Yeah. Yeah, it's amazing how fast C and Fortran are over Python.
Yeah. So you can see, I mean, when I ran it for 32 cubed, it was 100x, but now it's 1000x improvement of, or it's still probably 100x improvement from both of them. So that's where this library called Numba comes into play. I mean, Numba is just something I'm going to use, but then later on, I will show you that this is not just about Numba, but you can go further as well. So in terms of going from one layer to another layer and how the progression happens of GPU computing, I'm going to go for Numba. Numba has a lot of features. So the lot of features are basically it provides a JIT compiler, just-in-time compilers, and then it also has a vectorized operation, and it also lets me use GPU computing. So I can write code, compile it in such a way that it works in CUDA in GPUs basically. Okay, so till now when we looked at it, we were pretty much dealing with the like GPUs as if we don't know what is happening inside. We're just looking from outside how things are working out quickly and all. That's what PyTorch Lightning gives us, right? But we'll understand what goes inside in detail. So what I'm doing here is I am loading a number. And then once I do Numba, what I'm doing is I'm just going to apply @JIT, a decorator, to the Python function I wrote earlier. And then I'm going to, what do you call, once I do that, I'm going to do the maximum time it again for this one. Something happened. So I probably did not import this. Let me remove this guy. So there you go. So this guy, it works pretty quickly. So you see that the JIT compiler, because I compiled it, now is of the same order as whatever you got from the numpy np.maximum. I mean, one could argue that this is even faster than np.maximum, but that is just one particular case where that could be possible, but not generally. Again, vectorize is also something we can do where you're vectorizing the whole thing and then working on it, in which case it is much faster than whatever you got earlier. Now comes the part where we are going to use Numba for performing the GPU computing itself, right? So what we are going to do is we are going to see if the Numba's drivers, required drivers and all are present. And then I'm going to do the same vectorize operation, but on GPU. Okay. So I'm using the GPU, but still it is fast. It is slow. Can someone tell me why?
So is it the GPU built for specific types of calculations? And also the amount of time it takes to send data from the CPU to the GPU.
Yes. So yes, both the answers are related. So in terms of why we use GPU and all, so the idea is that GPUs can perform very simple instructions, but in a massively parallelized manner. So just like in CPU, you have multi-core, multi-threaded functions. In GPU, you have multiple cores and multiple threads, and these threads are millions in number. So that helps us in embarrassingly parallelize the computations and giving you results very quickly. But here's the catch. The catch is that when you're performing those computations, you need to transfer the memory from your host, the CPU, to the device, which is the GPU, and then back from the device to the host. So this transfer of memory from the CPU to the GPU and then bringing back is very expensive. So that is where we have to be very careful how we use the GPUs for accelerating our performance. That's why you don't see much of an improvement. It's fast, but it's not as fast as we would want when we are using GPU for a small task like just computing the maximum and for such a small size as 128 cube. GPUs can do parallel operations for much bigger matrices and all. Okay, so that's the idea of what we are using. So you can see the maximum 4 is something which we did earlier, the vectorize, and maximum 5, both of them are pretty much similar in terms of performance. And if you go further, you see that the maximum 4, maximum 5 is getting lesser than maximum 4, and you can keep going on further and further. So this is a study which one can do easily. So that's just about how to perform vectorization and all. So now GPU programming is in Python using Numba is a completely different thing. So where we basically can take threads, blocks, and grid. Basically, you can index each and every thread and block of the GPU. So GPU, as I said, has millions of threads, and these millions of threads are categorized into threads and blocks. So and a grid. Basically, there is a hierarchy. Almost around 1024 threads form one block, and I think around again 1024 blocks form one grid, basically. And these can be like 3-dimensional grids, basically. So there can be like 3 different dimensions of X, Y, and Z, and you are performing the grid, all the operations in a grid. So right now I'm getting some thread index and block index and all. And from this thread index, block index, I'm coming up with one unique index of the matrix, and I'm performing the operation for that matrix and storing it. So now when I'm running the data, this thing, all I'm going to do is I'm going to take in the threads per block and blocks per grid. I'll transfer the memory to the CPU from the to the device, that is basically to the GPU. That's a device. This is a pointer. And once I get those, I'm going to call the function with the blocks and threads which I want to use. And once I compute the maximum, I can copy back the data from the host, from the device to the host, basically. So that's the C. So this is the way one can perform GPU computing. So the reason why I'm covering about this whole thing is to understand how the GPU computing, underlying GPU computing, when you run a code in deep learning works when you're actually doing these things and all. So that's why I am going through all these different things and all. So do you guys have any question on how this is happening and all? Any question on Numba or how to write codes in GPU and all? So you can even, so just like I'm using Numba here, I can do further. So I just wrote maximum 6 till maximum 6 here. I can define a def maximum 7, which takes in A, B, and I'm going to use torch. So I'm going to import torch first. Import and then torch dot maximum of A comma B, and then if C is equal to that, and then return C. Now I can run the same thing here. So I can say time it maximum also, I think I forgot the syntax here. Oh, sorry. Let me double check the documentation once. There's a torch.maximum as far as I know. It says it's there. Ah, I know what it is. Sorry. So it needs to be a torch.tensor, or I can do torch.from numpy. So it takes about 84 milliseconds. Now I can do one thing that I can say a th dot CUDA and b th is equal to torch dot from it clearly is probably taking much more time than that, but you can see. So earlier it took 84 microseconds, but now it's taking 15 microseconds. So that's what you're gaining by doing all the operations in GPU, basically.
So I
So
have a
that-
question.
Yes,
So if you're writing custom CUDA kernels using
Yes.
C,
yes,
you have to use this global call to any function that you want to perform on the GPU.
yes.
So you don't need any of that.
When using number, no.
Yes.
That is all added by number itself internally. Yeah. So yeah, so again, as I was saying earlier, so compiled language. So there are two advantages we are getting by using PyTorch, which we are using for our all our deep learning purposes. One is that it's a compiled language. So all the codes are for PyTorch are written in C++ and CUDA. So it's all written in the base native languages compiled, and you're and well wrapped up with a proper API in Python. So now when we are using something in like torch.maximum and all, it's using the C++ functions. And when you transfer it to CUDA and run it, it's going to use the CUDA functions written from torch in C++, in CUDA C and all, and you are getting much higher performance by doing so. So that's why we use these libraries, because they have all these things inbuilt from long time back. So we don't have to rewrite all these things. For example, we don't have to write a CUDA kernel for performing the maximum operation in a GPU. Okay, so that's why that if you go to the torch documentation, you'll find a lot of operations. So if you go here, you can find several operations which you would be doing in your day-to-day life for any programming, and then all those things are available here. So you can do any of these operations on the GPU very quickly. So that's the overarching idea of what the GPU computing is and all. Any questions?
I have a question. So I thought when you ran that before, did it say 10,000 runs? And then it showed, so when you changed it to the CUDA, did it
Yeah.
do more runs?
Yeah, so
Okay.
the time at magic function in Jupyter,
Uh-huh.
if it takes too much, then it performs too less number of loops to
Yep.
give us the mean and standard deviation.
I
But
see.
if it is too fast, then it does much more.
I see. So because it was running faster, it ran more
Exactly.
of them to
Yeah.
build a bigger sample. Okay.
Yeah.
I was like, that. I understand that it's faster, but I was like, I swear it ran more loops. The last couple times you ran it, it was running more and more loops.
Yeah. Any other questions?
Are these CUDA standard if I change GPU brands or versions? Will those still run?
Beautiful question. So yes, it will still run. It will still have similar performance, but not same performance. So A100 has a lot more number of cores and much better. The hardware architecture is better suited for performing these tensor operations compared to a graphic card like Titan or even 1080. For example, laptops have 1080. They are more optimized for graphics rendering than for tensor operations. So you will see a significant improvement from CPU to GPU, but you will not see as fast as an performance as what you're seeing right now on a A100.
Yeah, and these, like, even though we're splitting these A100s across all of the users, there's still more RAM and more cores than on some of the older architectures.
Yeah.
And it's faster.
Yep. So you can always go here and check what are the GPU resources, utilization and everything. And also,
Yeah, when I ran that Boca Mini the other day, it was a little sluggish. It took a while to kind of wake up. So I don't know if it'll work or not. It does work, but it was weird. It would work sometimes, then it was blank other times.
Okay. So it's basically, I think probably because right now there's no active something utilized in the GPU. So that's probably why it doesn't show up anything. So yeah, any other questions? So once you have this thing, basically I have a couple of notebooks here. Again, it's the same thing as what we did earlier, but I'm just going to, I have this notebook just to show how we do the pipeline if you don't use any PyTorch Lightning or any other package and just using PyTorch alone. How do you do it? So for that reason, I have it here. So it's the same code, but all I'm doing is after downloading the data and everything, I create basically the data loader myself. So I create the torch.utils.data loader here, and then I create a model on my own. In this case, I'm just creating a simple 2-layer neural network. And I define as SGD with a simple stochastic gradient descent optimizer, the same loss function. So nothing changes there. Here is where I go through the every loop of what is happening. So what I'm doing here is I am running it for 20 epochs. I keep track of the train loss and everything. And every single time I have to transfer the images and labels I'm getting from the data to the CUDA. And before that, even the model which I'm loading here has to be transferred to CUDA. I must have done it somewhere. If not, I'll probably forgot. So it's lr.CUDA. So that will transfer it to the device. Again, another thing, if I am having multiple devices, then I don't need, and I'm going to send it to multiple GPUs, then I don't need, if I do .CUDA, it is going to always send it to GPU 0. So instead, there is another operation called toDevice, and then I can give a string CUDA 0. CUDA 0 is going to take me to GPU 0. It's always 0 indexed. So GPU 0, GPU 1, all the way till GPU 7 or 8 or how many. I haven't seen more than 8 GPUs in a single machine. Usually they don't do it, but yeah. So that's another way to send the model to the GPU. Once you do that, so you're sending the model to GPU, same way you're sending the data to the GPU. You perform something called as zero grad. Zero grad is something to help you in performing the back propagation properly, accurately. And then, so zero grad and loss dot backward, they go hand in hand. So you need to perform zero grad before performing the forward pass, and you need to perform backward after you compute the loss, and then optimizer dot step. And that way you're running this for several mini batches of data, and these mini batches finish, and then you run it for the validation step, and then you accumulate all the training loss and test loss together, and then you print it here the bottom. So let me probably run this tutorial from the beginning. Oh, so that means I need to stop this notebook. So another way, if you don't have such fancy things, usually what we do is we go NVIDIA SMI. NVIDIA SMI says that I already have 8 GB of GPU memory being used. I can always clear it. So
yeah, I saw this. I'm really interested in how this works, because I saw the same thing. I ran this and I saw it all, and it stays in memory. Why is it still in memory? Is it loaded?
Yes. So because I did .CUDA, but I never brought it back to CPU, right?
Oh.
So if I do sorry.
There's no like dump or.
I can do del, so it because PyTorch is well wrapped up with PyBind 11 and all. If I do del ATH, then it will delete the variable. Basically, the garbage collector will collect it. So this is going to bring it back to CPU. So I'm hoping that should bring down the GPU memory. It did not.
Oh, yeah.
So something else, maybe some other variables are storing.
There, 17.
So
it's the same name though.
I can just delete them and see what happens. Okay. So it looks like those are not there. Probably didn't run that. Anyway, let me go and.
Is there a way to force it from NVIDIA SMI? Why not?
No, you can shut down the kernels here, right? So you can find out which are what PIDs. So these PIDs are corresponding to each.
Yep. Oh, I see. Yeah, each one of that. So each of those PIDs is a notebook.
Yes.
Wow.
So, and you can basically control which PID is what and delete those basically. So you can do PSA UX grep 75714 and it should. I don't know why it doesn't show up. Interesting. Okay. For some reason it doesn't show up, but the PIDs should usually correspond to each notebook. So if I say shut down PyTorch inference, maybe, and then this one. Now, if I go back and so there you go, it removed most of the things. I still don't know why it is holding some 5 GB of GPU memory. But anyway, so this should help me at least run this guy. So training started. I can go back to the terminal and see now how much memory it increased. So you can see that earlier it had 7571483, and now 924924428 got added, which is
Aditya, can you run this one more time? I like running NVIDIA SMI with the space dash LMS and then space 500. So that dash LMS is it's 500. So it'll refresh every 500 milliseconds. Maybe if you reduce the size of your screen a little bit, what it's doing is it's showing you a new update every half second.
Mhm.
So you kind of have to you have to get it just the right size so that it doesn't flash. Yeah, it works better in real terminal. But anyway, I set that and I let it run, and then I can just watch it, and it every half second it refreshes.
I can do NVIDIA SMI this way as well, right?
Oh yeah, that'll be good. Same thing.
Yeah. Chisa, you have a question?
Yeah, I think I'm using the 15. I think that's because of the reason, like the memory was.
Probably.
Yeah, because I'm on 50. I'm on 15. I'm actually running stuff, so that's why I think it's because of taking.
I see.
Yeah.
Quite possible. Yeah. That increases my curiosity. So just a small detour. Okay. Some reason, some of the tricks I use in my personal machine don't work here. But anyway, so as I said, we do have the training running. So this one is supposed to run for 20 epochs. 16 of them have to be finished. And the loss value has gone down from 1 to 0.28. It's stagnant over there. Any questions?
I still have questions about how to destroy things. So how can I clear that stuff out of RAM from the terminal? Is there an NVIDIA command to clear the PIDs, or do you just want to do?
No, so every PID has to be, you have to take the PID and do kill 9.
Do what you're doing there.
Yeah. So you have to do a kill 9 to kill the.
Yeah, that's okay.
So I see that. Okay, so I can go.
Right.
I
But
don't
there's
know.
no purge or anything or
Yeah. So I'll have to do kill 9.
Yeah.
7 5
That's
7
my
4.
normal way. It might have stopped already. Yeah.
Something. Anyway.
Okay.
What I can do here is, because this GPU, this one I have control over. So you see it, this one is still having 1914, right? So
Yep.
if I now do LR, what's the model? Net dot to CPU.
So you're dumping it off of the CUDA RAM now.
Yeah. Let's see if that brings it down.
It's gone. Is it gone? Something disappeared.
No, it didn't. Still here.
Huh. Is it because it's still running?
No, it ran, so it got over. So Dell images. Some reason it doesn't work.
Are those your processes, or is that the other person's on the machine?
No, it's mine. I am sure because I killed this. So if I shut down this guy, which is the kernel I had, there you go.
There went one. Okay.
So it is the same process, but for some reason, it doesn't remove the, it doesn't free the memory this way. Usually it does when I'm running it. So let's try this. So I do have another code, right? So notebooks part 1. In the deployment, I had a MNIST thing. So Python, PyTorch, MNIST training. So when I'm running this guy, it will have a proper PID, which I can keep track of. So if you see now, it says it's taking 2000 MB.
Yeah.
And I can do a watch, and you see that as soon as that process gets over, the training is over, it will free the memory. So
That's nice.
So I think the Python's garbage collector could create some problems once in a while.
Yeah. And I've always wondered this about that. So the volatile GPU utility there on the right of it, is that the actual core activity, or that's just the up and down on the number of processes? Like, is that like the Z-score or something?
It's the core activity. So how many cores are being used at one particular point?
Okay, so it is only using 5% of the GPU right now.
Yeah, yeah. Because I mean, this is a very small model and very few number of operations in terms of convolutions and all. There's rather no convolutions at all. It's a simple linear regression model. So literally there won't be any much use of cores. Any other questions? So this should end in epoch 10 now. And then we can go to the next part. Yeah, there you go. So now the memory is gone. Cool. So that's that. And then now let's go to the next part.
Yeah, I just have one
Yes.
question. So normally when we tag the PID, what they run is use the PS command, right? PXE rex.
Yes.
Oh, sure. Okay, thank you.
Yeah. So yeah, so that's that. All right, so this is just about how to use it and everything. So sometimes I think Tyson didn't talk about it probably on how to get these the Jetstream resources and all and so basically you will probably get it from applying for a so it's there in this thing. So
Yeah, if you go to the yep. So I've put a couple of self steps for any of you that want to get an allocation on Jetstream 2. The first step is to get an account on Exceed, which is the National Science Foundation's service for managing these public resources. So you get an account on there. You then submit. Typically, it's only a 1 or 2 page justification for why you need the resource. And startup allocations are reviewed, I think, weekly or every couple of days. So you can get access usually within 48 hours. They'll give you on the order of about 200,000 hours of CPU time. And the CPU time, the burn rate changes. So if you're running a full VM, you're using the equivalent number of hours per hour of however many cores are on that machine. So a full Jetstream 2 instance has 128 cores. So you'd be using 128 hours per hour. But you would have an entire A100 to yourself. So that's the back and forth. You can get research allocations after you've done a startup allocation. So you use those initial 100 or 200,000 hours to develop benchmarking for your research. And so you come back and write a larger proposal. They accept those quarterly. So every 3 months, they'll review those. And you can get an unlimited number of hours. So in the millions of hours for a research allocation on Jetstream 2 for multiple years. So that's my suggestion if you like using this. Aditya, could you click on the Exosphere interface button there? So there's so there's 2 ways to access Jetstream. So Aditya is using our allocation that we're on today. So you can see he's running all 16 instances. In that, do you want to click on that and we can see? So you can launch your own machine. Maybe you click on create and then a new instance, and we can see if we wanted to create a new instance. So these instances, you can use either Rocky Linux or looks like there's a Red Hat, and then you can select the size of the VM you want to launch. And depending on how many VMs you're already running, you can set the number of those and the size of the disk, and then it launches and then it's yours. And then you have Docker on there and you can start running this container or any other container that has Docker. So it's a really nice, simple way to get started with cloud using Exosphere. The service that we're running for this workshop is something that Edwin has built, which will be another UI called Cacao for continuous automation, continuous orchestration. And it's good for workshops. So we can launch a whole bunch of instances. We can put the same Jupyter Hub on all of them with authentication, and we can get all of you guys in here and run a class. So, and maybe even similarly, you could launch a Jupyter Hub or Kubernetes cluster and make a single massive supercomputer. So you could have many machines talking together, running distributed tasks on GPUs. So that's the Jetstream 2 stuff for anyone that is interested. And you're welcome to reach out to us for more information.
So thanks, Tyson. So yeah, so if you do not have any of these things, so in the flyer, I had mentioned that you could use Google Collab as well. So this is something people use in the beginning of the research when you just want to do some brief experimentation. So for example, you can run some of the codes for it. Let me probably do, I do have one notebook here running, or let me pull something up real quick, just a second. So this is a notebook I created using the same things which we just saw, but this notebook is going to run in the Google Collab. So Google Collab is also a good tool. So, but there are restrictions which we'll go to later on. So the way you'll run it on a Google Collab is basically you'll go to runtime. So first and foremost, you'll start with collab.research. So one step back. So let me collab.research.google.com. So the notebook I'm running is already there in the Google, so in the GitHub. You can always download it and then upload it here and use it. So you can either upload it, drag and drop, or you can directly give a path to a GitHub URL and then you'll be able to use it. Or you can use your own like IPython notebooks in your Google Drive and use them as well. So in this case, you see there are a lot of notebooks I have in my Google Drive, which I can use anytime. So these are some things I use personally when I don't need too many resources, but I just need something for testing out how the resources are working out, how my code is working out and all. So the way you do it is once you upload the notebook and open it here, you will so you'll first go to runtime and then go to change runtime type. So ideally it starts with none, but then when you say GPU, then there are some restrictions. So and these restrictions are basically you cannot run it for more than 1.5 to 2 hours or something like that. Earlier, 2 years back when I was conducting tutorials and all, I used to use a Google Colab for even a day, but they have been reducing the allocation more and more as we go along. So the GPU resources have been available, but limitedly. So once you set it up, you click on connect here. And once you connect it, you can run NVIDIA SMI. And in NVIDIA SMI, you see that it's using a CUDA, sorry, a Tesla K80, which is not a new machine, but a new GPU, but a pretty, I think 5 years or 6 years old GPU. And after that, you can run the codes just the way you ran it in the Jetstream 2. But here, you cannot use it for your day-to-day research purposes for a prolonged period of time. So, but this is always good for doing some initial experimentation, or for some tutorials or something. You can use this easily. So that runs the code. So another thing you can do if you don't want to use Google Collab is basically you'll have to probably run it in your own machine or something like that. So for that, I mean, most often these things are run on a Linux machine. So that's something I'll probably cover a little bit on how we can run it on a Linux machine. So that's something I'll probably do in a few minutes. And in Windows, you can do the same thing, but with a lot of other things which we could do. So right now, I'll probably stop for around 5 minutes. If you have any questions, you can, and like I can answer them. Otherwise, I'll probably stop for 5 minutes just to take some break, and then start on setting up the environment in Linux and Windows. And I think that's all I'll be covering today in the workshop.
Hi, Aditya, are you still there?
Yeah, I'm
So-
here.
I have another question. So
Yes.
recently I made a question. So when the time you run code, right? So I have one question is like, my GPU is not full, but my CPU is full.
Yes.
So how would you optimize like this situation? For example, I have code, but I use HTOP to check my CPU memory like usage, right? So my CPU is full already, but my GPU is not full. I still have like can run code on GPU. So how do you like optimize?
So for such scenarios, usually, you remember I was talking about in the part 1 training, instead of loading the data upfront. So what you're doing here is, why is your CPU memory full? It's because your data, which you are loading up upfront, is all in the CPU, correct? So instead of loading all the data in the CPU beforehand, like the way you are doing over here, instead what you would do is you would load only a part of data at one given point. You don't load the whole data, you load only a chunk of the data. So that way your bottleneck has to always be the GPU, not the CPU. Your CPUs can always, I mean, you can always do something to get the CPUs to run fast. So you don't want to limit yourself based on the CPU memory.
Oh, okay.
Does that make
Sure.
sense?
Yeah. So you just limit the size of your each time you load, right?
Yes.
Okay.
Yeah.
Okay.
So you don't load all the data together, because the data is what will usually take the CPU memory fully, completely.
Okay. Sure. Thank you.
All right. So let's get started with the last part of it. So till now we saw how we can run everything in an ecosystem which we have already created. So you didn't have to install anything and you didn't have to do anything to get this running. So right now what I'm going to do is I'm going to first show how to run how to create an environment to run all these things in a Windows machine, and then I'll probably take some time to show you how to do this in a Linux machine as well. So that's something I'll probably do now. Just yeah. So in Windows machine, there are multiple ways you can do the all your training and everything. So the way you do it is, if you are using a Windows 11 and a Windows 11 operating system or something, then you can use Windows subsystem in Linux, which even supports GPU computations and everything in Windows subsystem in Linux. So Windows subsystem in Linux is nothing but as good as you're having Windows with a separate terminal of Linux on top of it. It creates its own subsystem, it creates its own file system and all, and maintains everything. And you can share data between Windows and Linux. It's different from the virtual machines and other things which one would use, but that's one of the latest or best ways to do programming in Windows using Windows subsystem in Linux. So for example, right now I have a Windows subsystem in Linux, and I could install the other day the I commands and everything. So I can use iRods and do I init and everything as well. So if I do I init, I just have to enter my password, and then I can do ILS as well.
DT, can you make the text bigger? Thank you.
Yeah, so I did INIT and then ILS. I can always do ICD. So ICD and then to what do you call I/iPlan home, and then my username. And then if I do ILS now, it should show me. So I just have a folder on analysis, which I have run till now in discovery environment, and there's some temporary Python file, which I have over there. So pretty much I can run everything on the Windows subsystem in Linux. Now, how do I install other packages like Python and everything in here is basically using Miniconda. So I use Miniconda for all the maintaining all the packages and everything. So if I do which Python, it should show me the Python from the Miniconda, and I can create different virtual environments, Conda environments as well. So if I do Conda env list, then it should show me all the different environments which I have in my this thing, Conda, like in my WSL. So this is one way you can do programming in Windows. Now, this is not the only way. So I can do programming so in Windows natively itself. So there is in Miniconda, there is a Windows binary and Linux binary as well. So if I go here and look for installers, there are installers for Linux, Mac OS, and Windows, all three of them. So I have a Windows installation of these things as well. So if I do Conda and list, it will show me several other Conda environments which I have over here. So if I do Conda and Conda activate ML flow test, it's going to take me to my one particular environment where I have some things installed. If I do pip list, it should show me all the packages which I have installed in here. So you can see that most of the packages which we were using, even the Jupyter Hub and everything, is there here. Numpy, and yeah, so most of the packages should be there. So if I can do Jupyter Lab or even Jupyter Notebook, then it should open up a Jupyter Notebook in some place. So there you go. So I can run things here. I can always so I do those things and all. So that's the way you can run it in. So I can go new, probably not in this one. Let me move to another environment where I have Torch installed. Conda deactivate So now I can run import torch. Some reason. For some reason, it is not working for me. Probably let me try some other environment. I do have. I must have messed up something. So this is how you install Jupyter. I didn't want to cover that, but it looks like I have to do it. So there you go.
So I also have a question on this.
Yes.
So for install Jupyter, I think it's same as Spider. So you need to install for every environment, correct?
Yes, that's correct.
So is there any way I can install on my Linux version so work for every environment?
I didn't get that. So
So
you want to install Jupyter Jupyter Hub for all the environments?
So install for every environment, I install locally on my Linux machine, and for each environment, it automatically opened by the Jupyter install on the local machine.
So
To do it.
No, it is. I mean, you need the Jupyter, so you can use your basic. So whenever you create a new environment, it is going to copy the base environments, whatever, however you have defined the base environment, and it would use that. So if you have Jupyter notebook installed in your base environment, then there is a possibility that those things will be always also be transferred to your whatever environment you are creating. Okay. Now the problem with Jupyter Hub is that you don't want to do it that way, because you want to have the packages kept independent of each other.
Okay. Sure. Okay. Sure.
So while this is running, probably I can go and show you how to do this same thing in a HPC environment as well. So in an HPC environment, you can access it in either using a WSL or using a Linux like a shell like here, or using Windows. Either of them will work, but you need to basically SSH to the machine. So for example, I can show how to do this over an Exceeds a cluster, which is a supercomputing cluster in Pittsburgh. So Bridges 2 is a cluster in Pittsburgh Supercomputing Center. So I'll be using that for showing this. So I'll SSH there, and then I'll have to add my password. So once you enter into an HPC cluster, basically you'll have to look for modules. So most of these use modules for everything. But before we go there, you also need to allocate a GPU. So the way you do it is in Bridges, you use something called as an interact, because a cluster has many nodes and you want to use the compute GPU nodes in such a way that you are able to use them properly. So the way you do it is by using an interact command. So the way you can do it is you're asking for one node and the number of cores is say 128, and then say time you are requesting is say 020000, and then that's 2 hours. And then you need to also provide a command for this thing. So GPU, let me tell you that. So you need to also add this thing, aggress GPU, and then so V100 16, and then how many? So you need to specify one. I think I have access to only 32. So this will queue one such node. Okay, so for some reason it's okay. -p GPU. So again, if you don't know what is it that you want, basically you can do sinfo. That will tell you all the available nodes and what is the time limit and how many nodes are available, what's the state of these nodes, and then you can basically take a thing. So you all you want is basically a GPU. Just a second.
Do you need your, okay. So do you need your username in there? Or your
Which one?
account? Your
No, account
add
is
your account?
fine. I think that's not the account the problem. It's the problem of Gress. I need to give the for some reason. Oh, so allocation requested CPUs per GPU higher than 5. Okay, so I need to ask for 5. There you go. Whew. So now that the allocation is granted, basically you'll have a GPU for yourself. So if I do NVIDIA SMI, you see that there's a Tesla V100. V100s are slightly older than A100s, but they're also really good in terms of this thing. And then you get a whole Tesla V100 for yourself. So now I can, so if I want to run anything here, so all I have to do is module load Anaconda 3. And then I have to do conda and list. So I should have some environment which I have already defined here. I just hope that it works. Conda activate. And then if I do Python, and then I can quickly wget the code I had in the Git repository. So and then I can do Python, PyTorch, MS training, and it should start running.
Missing amount form, yeah.
So DJ, that's one thing I think we should do for next time is we need to have a really bomb-proof environment YAML that
Yeah.
has everything in it.
Yeah, I agreed.
Getting there.
Yeah, so this should work. Yeah. So does anyone have any questions on how to do these things and all? Right, I think that's pretty much what I had for covering for today.
Okay.
Just in terms of all the different environments, setting up all the environments. Unless anyone has any questions, I think I'm done pretty much.
Means we're almost done.
Yeah.
Aditya, I have one question.
Yes, Zaid. Yep.
Yeah, so is there any way to extend the time limit when you are like
On an HPC request?
yeah, yeah.
I don't know.
Like if my model is running for too long and that exceed the time limit, then what
Right.
will happen?
Yeah, so there
Oof.
are ways to do that, but usually like Slurm doesn't allow that. So you'll have to requeue your job again so that you can run it. That's one thing. And the second thing is this Slurm has another thing that you can auto requeue every single time. Once your job gets killed, you can auto requeue and you restart from wherever you left.
Yeah.
So these are two things you can do.
Another risk of running on HPC is being preempted.
Yeah.
So you could still be on your scheduled time, and then some other super user does priority, and you get
Yeah.
stopped.
Yeah.
Oh, yeah, I understand. Yeah, thank you.
Yeah. Any other questions? I'll probably stick around to see if there are any other questions, but yeah, pretty much this is what I had to cover today.
Yeah, and I'm here to answer any questions you guys have about running these analyses in either the discovery environment, which we didn't really do today, but can be done, or questions about using Jetstream.
Yeah, I have one more question. So when the time I use the ML flow, so when you extract the environment,
Yes.
So would it be able to rename the environment when you extract? Because when the time you use the server, correct, you copy down the address
Yes.
and then environment, but the
Yes.
name is predefined. So would it be able to rename the environment when you?
So I think it is possible that you can rename the environment. But I mean, the environment which you're creating is local, so you can always do those things. So there are actually even methods where you can create a server without Conda and just using pip virtual environment and do those as well. And you can create using Docker. So you don't need to have the same name always. So that can be done.
Oh, okay, sure.
Those are different options you can provide to. So when you say ML flow models serve and then you give the model path and all, right, you can give different path. So you can do -h and it gives you a lot of options you can use for ML flows model. So yeah.
Sure, I will check on that. Yeah, thank you.
Any other questions?
Well, thank you guys for sticking it out. The survivors that made it till the end.
Yep.
Carlos, thanks for coming. Hopefully you got something out of this.
Sorry, Tessa, I have one more question. So every time I log in, for example, now you guys sign me as 15, correct? So I always log in as the virtual, like the virtual machine as the local, correct? So every time I finish the code, just now I asked I need to use the I push, I think. I push.
Yeah, so that's if you want to keep
Yes.
your results from this Jupyter Lab, you have a couple options right now. You could download them from the Jupyter Lab. You can like right click on files and download them to your laptop.
Okay.
Or you could probably use the IPut command to push them to your data store. And you would do the IPut, the name of the file and the path. On
I already did the IPut. So I'm just asking, is there any way to like automatically upload when I finish, or just every time I have to do the like IPut or something?
You would have to do it because we're on Jetstream, which is in Indiana, and Cyverse, which is in Tucson and in Texas, you have to move it off.
Oh, okay.
If you had run this in the discovery environment with a GPU, you can run it on a CPU only, but on a GPU enabled Vice node, then your analysis folder would get the analysis when it finishes. But we didn't do that in Cyverse today because Cyverse doesn't have 40 VM capable GPUs to get on the fly for everybody. So it was easier for us to go to Jetstream. Jetstream is brand new, so it's the best equipment out there. So it is a better resource for you to think about using.
Okay.
It's also a good time to get in because nobody knows about it yet.
Yeah. Yeah. Thank you. Appreciate it. Yeah.